Yeah, so we'll start today's discussion. So, if you look at the topics covered in the class in the last week or so, or week 6 of the course, you'll observe that there was a lecture on method of Blasius for flat plate boundary layer. So, I think one of the initial classes, when I discussed briefly about similarity solutions, I said that we'll use this again in boundary layer. So, this is where it again props up, and it's not like the similarity solution is only uh, existed for boundary layer analysis or something like that. It is very widely used technique, and basically Blasius started it. So he was like the first guy to use the similarity solution or similarity variable in the case of boundary layer, because we'll see out the brief history, but then this method got very famous and it's used very widely uh, for some problems where one of the length scale in your domain is not bounded, like that. So I'll just give some pointers on the Blasius similarity solution, because that was discussed in one of the class. We'll not spend much time because sir has professor has derived and for hydrodynamic boundary as well as thermal boundary, etc. You get different scalings from this. So uh, some things about Blasius method. So it's nothing but a similarity transformation. So what happens? Even before going there, how did the Blasius got this intuition? So what he did, I think he was a PhD scholar when like a long time ago, but he was working on this boundary layer problem. And what he did, he conducted a couple of experiments, and he plotted a curve which on x-axis you take uh, u divided by u infinity. U is the velocity at any particular location in the boundary layer, and at that particular x, you plot that u by u infinity ratio against y by delta. Delta is the boundary layer thickness, and what he did multiple experiments with different Reynolds numbers. But this is like for laminar regime only. But within laminar regime, he did experiments with various uh, Reynolds number. And what he observed is, for each experiment, you get more or less similar variation. This is not like you get a single line, you get this curve by curve fitting. But you get the point, right? This is where he got the intuition that maybe this variable is related to this variable somehow. And then he assumed this variable as your similarity variable, which typically is referred to as u eta. And then what you do, basically, you uh, assume this as some function of eta that you don't know, that you want to find out. And then you take the help of your governing equation, especially your continuity equation and momentum equation, that you already know how to do that. And there are various terms in those, uh, you know uh, so basically, uh, this eta is y by delta. And if you assume this similarity variable of eta for y by delta, what you do, you combine two variables which are y and delta into one variable. And choice of such similarity variable should be such that uh, your boundary conditions are also satisfied. So what are boundary conditions in boundary layer problem? So basically, uh, you know, at y equal to 0, your theta comes to 0. So at y equal to 0, your boundary layer thickness is 0, right? So theta is also 0. Whereas, one second. Yeah, so when your y reaches delta, or y approaches your boundary layer thickness, your eta value goes from 0 to 1. So you have a variable which varies from 0 to 1 within a boundary layer at a particular location. And then what you do, you assume such function which is f of beta, and then you calculate del u by del x, del v by del y for continuity equation. So for example, del u by del x will be nothing but del u by del eta into del eta by del x by chain rule of differentiation. And then right, u is nothing but here u is nothing but u infinity into some function of eta. So you take the derivative with respect to eta, and this del eta by del x will be nothing but y is not a function of delta, y is not a function of x, but delta is function of x, right? Which is boundary thickness. So therefore, when you take this derivative, y comes out of the derivative, and you get this thing 1 by delta. So minus 1 by delta square into d delta by d del x. So this term will get. So like that you do for all the things. And for x momentum equation, you use, see, you have x momentum equation, right? Which is nothing but, I'm not going into details because we already discussed these equations in last classes. This comes out to be second order term here, right? And then what you do, you already calculated all these derivatives, and then what is unknown here is v. So this y component of velocity, you get it from here, and that will be in the form of f prime, something like that, f double prime, because these derivatives are like that only. So basically you have this form minus u del u by del x divided by del u by del y, and then you put all these similarity transformation variables, and then you solve. So what happens in the end, you'll get a equation where you'll have so I'm skipping some steps because it will take a lot of time if we discuss those. But in the end, what you get on one side of the equation. So you know what I mean. You take this v and put it back in continuity equation, because in continuity equation this is unknown, right? This you can't find so yet. So therefore you put this v and take derivative and put it back in the this continuity equation. So basically this del v by del y, and then what happens when you further simplify the things, you get on one side of the equation you get one set of terms which is only function of theta. So or I should write function of theta, and you get another set of terms which are only function of x. So basically you get then you use a separation of variable method, and then you further solve it. So I'll not go into the details here, but what you basically end up with is, and this set of this one side of the equation where you get only what you call only terms which are function of eta. That is nothing but a famous Laplace equation. That is what I wanted to discuss here. Equal to 0. Yeah, this is what is called as, and from here you get scaling for x, which is nothing but this thing. Your what you say, your x is a function of what you say. This delta is function of delta by x is function of proportional to Reynolds power x power minus 1. That is that scaling that you get from this other term of x. But this is what this famous Laplace equation is here. This highlighted by this box. And then what you do, whereas this f here, where f is nothing but integral of that f of theta d theta term. So like that. And 1 second, there was actually direct question on this in your GATE exam previous year. So basically what they did, they just mentioned that for that matter, I'll just directly write this function. 1 second. Yeah, so basically the question was, this is previous year GATE exam question, and it was, I think, 2015. So if you don't know the form of Laplace equation, you can't solve this type of question if it comes across to you. So the question is, the Laplace equation related to boundary layer theory is, and you have first option, which is third order PD. Second option, there was third order linear PD, and then there was second option, which is third order non-linear PD. So like that, you had other two options also, second order non-linear PD and second order okay. So this was not PD, this was ODE, ordinary differential equation. PD means partial differential equation, ODE means ordinary differential equation, and this was second order linear ODE, something like this. Anything is there, because this option is anywhere not correct. So you should know at least the form of Laplace equation, so that you can answer this type of direct fact-based questions. So now I hope you know what is the degree and what is non-linearity, linearity, what is ODE, PD, those kind of terms that are frequently used in the course. Not only this, but various courses. So basically, you must have studied those in your math class somewhere. So from this equation, Laplace equation, you can say this is third order equation. That is because you have this term, which is third order derivative of f. Then you have non-linearity, because these two terms, they are basically let's say y into y double prime. So that's where non-linearity comes. And what do I mean by non-linearity? Let's say you replace y by y plus y1 plus y2. So basically additive properties will not hold, because when you multiply the two variables, there will be a cross multiplication term, and this is the source of non-linearity. So this is non-linear. Laplace's equation is non-linear. And whether it's ODE or PD, that now the thing is, now the confusion may come that whether it's ODE or PD, because see, it is 1 second. Uh, yeah, so this is OD because your f is only function of theta. Some people get confused here because they assume that theta is function of x and y, therefore f is also function of x and y. No, because f doesn't know what theta is made up of. It only knows theta. So therefore it is OD. So this is third order nonlinear OD. So yeah, I think this option, this was OD. So maybe the options are jumbled up, but you should not get confused here. The correct answer is this one. The point that I wanted to convey here is sometimes in exams they directly ask you some fact-based questions, and if you don't know the form of Blasius equation as given here, you can't do anything there. So that's why. So remember this form. So it is uh, third order non-linear ODE because it is only function of theta. So that was one thing that I wanted to convey. Apart from that, yeah. So this equation, Blasius equation, you cannot solve it analytically because it's a non-linear equation that to third order. So typically, uh, you can use numerical methods, and there is one method called a shooting method. So uh, what they do is they assume some initial value, then they check the residue, something like that. Exactly, you can go and check about it, but it's called a shooting method. And what they did, what is observed after solving this using that method is you get something like this curve where on x-axis you have beta and this is your f of beta equal to 1. That means u by u infinity is equal to 1, and you get this at beta value of approximately 5, and that's where your y beta is nothing but y by delta, right? So therefore as y tends to beta, your beta tends to 5. This is what the solution says. So then you take this information and you put it back into this function of x that you got, and you get the proportionality constant. So therefore you achieve, you get delta by x as 5 into rex power minus 1 by 2. So basically here you got some scaling, right? But exact constant was not known, and that constant you get by using this solution from the shooting method. And this is the famous result from the Blasius equation. And then they put this into, they calculate result number, CFX, etc., based on this, because then you assume some velocity profile, etc. And that is what I think the majority of Blasius method is there. So basically, it's a similarity solution and separation of variable also you use, and it's a third order nonlinear ODE, and you use some sort of shooting method, etc., numerical methods to solve or to get the exact solution to this method. You cannot do it analytically. And this is what the famous Blasius result is. So that's about it. So we'll move on to the next part because see, finally we were introduced to some, you know, correlations, and because mostly the numericals that you get are based on correlations only. So we'll start with some numericals. So 1 second. Okay, so there is one question. So yeah, and I think similar type of question is in your assignment number 6 also. Let me just check once. Drag force, chip, etc. Okay, okay. So we'll skip this one. We'll take some other question. Okay, so this is a. We'll start with some easy question. For a fluid with, let's say, Prandtl number 2, I'll just mention Prandtl number here. Prandtl number 2 at 500 Kelvin flows over a flat plate of 1.5 meter length, maintained at 300 Kelvin. So your plate is colder than the fluid. The flow velocity is 10 meter per second. So this is your U infinity. Assuming kinematic viscosity, which is gamma or nu, sometimes they call it. This value is directly given. What is the thermal boundary layer thickness at 0.5 meters from the leading edge? So this was a data entry type of question, and you have to, at this boundary layer thickness, you have to enter in mm. They had mentioned that. So now here you need to pay attention to this keyword, which is thermal boundary layer, because that is the important keyword here, because sometimes people miss that. They see easy question and they just miss a trick there. So how do you solve this? So what you basically do is you first of all calculate the Reynolds number in case in any problem related to this course, wherever convection is there. First thing you have to do is you calculate the Reynolds number to check whether it's laminar or turbulent, and based on that you use various correlations, right? So that is your first thing. So this will be U infinity into x by nu or gamma. And they had mentioned that at 0.5, right, from leading edge. So you just put this 10, this 0.5, and this is 30 into 10 to the power minus 6. So if you do the calculation, it's basically 5 by 3. So 1.66 will come, and it is basically 1.67 into 10 to the power 5. So since Reynolds number at x equal to 0.5 is less than 2 to the power 2 into 10 to the power 5, we assume the flow is laminar. In some questions, they directly mentioned if flow is laminar or turbulent. In that case, you don't need to find Reynolds number. So directly you can use the correlation for laminar or turbulent flow. So now they are asking about boundary layer thickness, right? So just now we solved this problem where using Blasius method we got as 5 Rex power minus 1 by 2, right? So now you put x equal to 0.5, Rex you already calculated. So basically you will get delta, which is 5 into 0.5 into 1.67 into 10 to the power minus 5 raised to minus 1 by 2. Correct. And if you do this calculation, you should get the answer as 6.124 into 10 to the power minus 3 meters. But this is your hydrodynamic boundary layer thickness, right? They are asking about thermal boundary layer thickness. So we know from previous class that del by del T is nothing but scaled as Prandtl number power 1 by 3. So now you have to use this delta already you calculated. Then you have to use this Prandtl number, which is given as 2 in this question, and you'll get final answer. You can do the calculation. Otherwise, give me a second, I'll do it. 2 to the power 1 by 3, right? So 0.333. So that is 1.26 basically. So 6.124 divided by 1.259. So you get 4.864. So this 10 to the power minus 3, I just converted it to meters correctly. So like this, you have to go about the questions. You have to use multiple concepts. So this relation between Prandtl, the correcting factor of Prandtl number for hydrodynamic boundary layer thickness and thermal boundary layer thickness, we learned it in the last class. Correct, no? Del by del T. Yeah. So now there is another set of problems which typically is asked from this type of uh, flat plate problems, and let me just find it. 1 second. Yeah. So this is also previous year gate question. So in this question, they have mentioned that there are two fluids, P and Q. So they have not mentioned what the fluids are, but let's say they are assuming it as P and Q symbols for the fluids. Reynolds number for flow over flat plate is 10 to the power 3 and 10 to the power 4 for fluids P and Q respectively. So they have given you directly Reynolds number, and you can see here this is a flat plate flow and it's less than the Reynolds number or less than critical Reynolds number. So this is a laminar flow case. And they have mentioned that Prandtl number for fluid P is 1 by 8, so less than 1. Or we should not go there because then the scaling will change. So let's say we'll take some other value, which is let's say your Prandtl number is 2 for fluid P, and Prandtl number for fluid Q is high Prandtl number, so let's say 30. So this is also given in the question. Okay. Now what the additional information is also given, which is regarding the uh, boundary layer thickness. Or in this case, you can make it a, what should I say? Uh, 1 second. I'm just trying to make another question out of this. So, straightforward, the first part of the question is, then what is the ratio of Nusselt numbers for fluids P and Q? So this is the actual question. So basically, in this type of questions, you should know first hint is since Reynolds number of fluid P as well as Reynolds number for fluid Q are less than 2 to the 10 to the power 5, therefore laminar flows. Correct. And for a laminar flow over a flat plate, we know that Nusselt number is nothing but, let's say we are talking about average, so 0.664 RE power 1 by 2, TR power 1 by 3, right? So then you can just use this expression because it's a laminar flow, and then you can just take the ratio. So for Nusselt number for fluid P and Q, the constant will get cancelled. So it will be just the ratio of Reynolds number for fluid P, Reynolds number for fluid Q raised to 1 by 2, Prandtl number for fluid P and Prandtl number for fluid Q power 1 by 3. So in this case, they have given REP as 10 to the power 3 and REQ is 10 to the power 4. PRP is 2 and PRQ is 30, like that. So this is 0.1 square root. So 0.1 sorry 0.1 square root. So the first term is 0.316 into 1 by 15 cube root. So 1 by 15, which is 0.0067, and we need to find the cube root of this guy. Sorry. Okay. So 0.0667. And you need to find cube root, so 0.33. So this term is 0.406. And you multiply this and you get the final answer 316. So basically 0.128. So this is your answer. What I wanted to try is maybe next part of the question could be, so this was the total question that was asked in the exam. Numbers or figures may change, but the idea remains same. So idea is you need to find which flow regime it is, and then you use the suitable correlation, and then you get the answer. So that will be the broader theme in this class. Okay. So what I wanted to tell you is, yeah, before going to other correlations, if you had missed some correlations in the class, I'll just write them down here so that uh, 1 second. Yeah, so these correlations, you should know like some of them. So yeah, you can take it as a note. You may be knowing all of them, but just for the sake of this class, for laminar flow over a flat plate, Nusselt number is at any location x is 0.332 Rex power 1 by 2 Prandtl number power 1 by 3, and your average Nusselt number till that point will be twice of your local Nusselt number. Then your skin friction coefficient is 0.664 by Rex, and your average skin friction coefficient is 2 times of your local skin friction. See, these itself are some competitive exams questions, okay? They directly just ask you, what is the local Nusselt number for laminar flow over a flat plate as compared to the local Nusselt number. So average divided by local, something like that they'll ask. And in case of mass transfer, you just replace Nusselt with Sherwood number and Prandtl number with Schmidt number, and this correlations remain same. And usually this is for Prandtl number greater than 0.6. So typically for air and water we use these. For liquid metals and all, for laminar flow, laminar flat plate flow, but Prandtl number less than 0.6. So this is case of liquid metals. It's a very rare case that you'll be asked this, but you should know that in this case the scaling changes. So maybe I'll put some star marks here, and in this case your Nusselt number becomes 0.565 Re power 1 by 2 PR power 1 by 2. So this is the change, and I think in the last class when I did the scaling analysis, I did this scaling also for low Reynolds, low Prandtl number regime and high Prandtl regime number regime. Then there is some general formula, etc. Don't need to remember those things. But the other important thing is turbulent flat plate flows. So here the thing is so this is when your Reynolds number is higher than your critical Reynolds number. So in this case your Nusselt number is 0.0296 Rex power minus 4 by 5. Oh, sorry, it's not minus, it's 4 by 5 Prandtl number power 1 by 3. And your average Nusselt number, it is not twice in this case, it's 0.037. So this is one important thing that you should remember. They become double only in case of laminar flow. In turbulent they don't, because these are all curve fitted correlations. In case of turbulent, it's very difficult to get analytical solutions. So they usually do a lot of experiments, and based on those experiments, you get the numbers. And this CFX is 0.592 Rex power minus 1 by 5. You should all at least remember these powers of the various numbers. So this is valid in this region only. So if it is in some other region, they'll give you the data. So like that. So there are a lot of correlations like those, and in some problems there is a case where you'll have a long enough plate like this, and initially your flow will be laminar, then there will be a small transition flow, and then there is turbulent flow. So this is laminar and this is turbulent flow. turbulent flow regime. You'll have different boundary layers. So in such case, what you do is you assume the assume transition flow regime is small, and you directly calculate your average heat transfer coefficient as the summation of uh, 0 to x critical. So this will be your x critical, right? Where your flow changes from laminar to turbulent. H of laminar into dx plus x critical to L H of turbulent into dx. And this you get from correlations, result number correlations, right? So this is a standard way to do these things, and once you get HL, you get your average result number expression as HL L by K of fluid, like that, no? Like that. And there is one more. I mean, usually you can just calculate this way, or directly if you want to remember something, this correlation is there. But I would advise, essentially you are doing the same thing what this integral form represents. So this is your laminar contributing term, and this is the term coming from your turbulent flow regime. So the thing about this is this integral if you do, and you get this final form of the equation. If you remember this, you can use it, but typically I have observed that you don't remember things after a long time. So you should remember that sometimes the flow may not be fully laminar, and in that case you may have to find till what point it is laminar and then use the uh, turbulent flows for the rest of the length. So one second, there was a question on this. Let me just see. Yeah, I think it's a conventional type of question. Let me just see. I had written down the numbers. 61. Yeah, so this is the question. So they have given a plate, that plate, which is at the plate temperature is, let's say, 150 degrees Celsius, or instead of, this is usually we refer it as wall temperature, right? So this is TW, and there is something like this usual setting. You have U infinity as 12 meters per second, and T infinity as 30 degrees, and this is air. So air is flowing over a hot flat plate. Length of the plate is 2 meters. Okay, that's it. I mean, that is the whole information that is provided. And now it is asked that find the local heat transfer coefficient at 0.5 meters from leading edge. So this is a typical first question is there. And same, find local heat transfer coefficient at L equal to 2 meters. So basically at the end of your plate. So that is called as trailing edge. So they have asked two questions from the same problem. So now first you should always check what is the Reynolds number at the interested locations when they don't mention any laminar or turbulent. But before that, there is some additional information given at mean temperature of 90 degrees Celsius, air properties are given. They are as Cp is 1.01 kilojoule per kg degree Celsius. Density is 0.962 kg per meter cube. Thermal conductivity is 0.031 watt per meter Kelvin. And your dynamic viscosity is 2.131 into 10 to the power minus 5 kg per meter second. And they have given equations also. So you need not remember equations also. Use equations. I mean, these equations you already know. Just now I give them as the note for laminar. And Nusselt number of 0.0296 RE power 4 by 8 for turbulent. So everything was given in this question. You need not remember the expressions also. So first thing everywhere is find Reynolds number at, let's say, first they are asking, about the 0.5 meter mark, right? So for that you need Reynolds number, that will be rho u into x by mu. So rho is given as 0.962, u infinity is 10 meters per second, x is 0.5, and your dynamic viscosity is 2.131 into 10 to the power minus 5. So if you do this calculation, you'll get Reynolds number of 2.7 into 10 to the power 5. So yeah, and in this question they had mentioned that assume this critical Reynolds number of 5 into 10 to the power 5. So see, there is this doubt in some problems, they mention a critical Reynolds number as 2 to the power 10 to the power 5, 2 into 10 to the power 5. Somewhere they give it as 5 into 10 to the power 5. So usually you take something around 10 to the power 5. So 2 into 10 to the power 5 is better approximation. But sometimes they give directly in the question, so you take that. So in this question they mentioned it should be less than 5. So since it's less than 5 to the power 5, it is a laminar flow. So you'll use laminar correlation, right? Laminar flow correlation. So this is your h x by k of fluid, 0.332. Rex we just calculated, and Prandtl number is nothing but mu Cp by K, right? So all these values are given, and if you put all the values and you get the H, I'm skipping a step here, you can cross check the calculations. You get H as 9.49 watt per meter square. Now you can see here only, right, before going to the second part of the question, at x equal to 0.5 itself, you are reaching Reynolds number which is quite close to the critical Reynolds number. So when your x will become 4 times, your Reynolds number will again become 4 times, right? Because it's directly proportional to your x. And in that case, your Reynolds number at the trailing edge, which is x equal to 2, will be nothing but 4 times your Reynolds number at x equal to 0.5, right? So that will be 2.7 into 4. That is 10.8 into 10 to the power 5, which is greater than 5 limit here. So this is a turbulent flow. So what is happening is, till certain length over the plate, flow is laminar and then it is becoming turbulent. So here you use turbulent turbulent correlation for local heat Nusselt number. You already know Reynolds number at x equal to 2. You use it, and Prandtl number you calculated in the before question. You just plug it here, and you should get heat transfer coefficient value as 27.36 watt per meter square Kelvin. You should note one thing. See, in laminar flow, you are getting heat transfer coefficient of around 9.5. And in your turbulent flow, you are getting it around 27. So that is typical case actually. In turbulent flow, you'll always get higher heat transfer coefficients. So because there is a in laminar flow there is predominantly the heat transfer is because of conduction at the interface, and then it is just advected to the bulk of the fluid. But in turbulent flow, there is conduction at the interface, that is the source of your heat flux. But there is not only advection, but there are vortices. So due to additional mixing and other turbulent turbulent flow regimes, there you get proper mixing, and that's why the heat transfer is very fast in turbulent flow. Sometimes in interviews they ask this question. And to the extension of this question, I can just add one more question. At what x does the flow become turbulent? So in some question they ask this question also. At what x the flow becomes turbulent? So here you have to find the x where your Rex is 5 into 10 to the power 5, which is your critical Reynolds number in this problem. So if you do that, you should get x of 0.923 meters. So at this x, your flow becomes turbulent, or transition of flow occurs at this distance from the leading edge. So this is a typical question. So then there is one more question. Yeah, so this question is also similar question is asked in your assignment. That's why I thought I'll take this. So typically, when we studied the extended surfaces or fins, there we assumed what you say, this thing. Yeah, there was this in the governing equation. There was a m multiplier, right, which was under root hp by k, and there in those problems that we solved, the h value was given. But now, since you know how to calculate h, which is your heat transfer coefficient, there is a standard problem in which what they do, they'll give you a fin in a fluid where there is a heat transfer taking place from the fluid, And first part, they will ask you to calculate the heat transfer coefficient, and using that heat transfer coefficient, in the next part of the question, you have to calculate the heat transfer from the fin or fin efficiency, fin effectiveness, all those type of questions. So we'll take one question like that also, because I think there is a one question in your assignment which resembles like that. Yeah, so in your assignment there is a fin, and they are saying that assume the turbulent flow around the fin, and in that case you have to calculate the heat transfer rate from the, or heat removal rate from the fin. So as I said, first you need to calculate the H, and then you use the fin problem, the fin correlations to get the heat transfer rate. We'll do that problem now. Not the exact problem. We'll change it to the change it somehow. Yeah. So let's go. So there is a you can call it a wall or something, and there is an extended rectangular fin coming out of this wall, and if you look at it from the other angle, it is a rectangular cross-sectional area, something like this. Okay, so it is a square, not a rectangle, sorry. So this is 4 mm by 4 mm kind of fin, square cross-sectional area. Your ambient is at 27 degrees Celsius, air, and it is flowing over the fin with velocity of 10 meters per second. And it is cooling. Basically, it is fin mounted on a electronic device. So this is the electronic device interface, and your fin is supposed to cool the electronic device by rejecting its heat. And heat rejected by the fin to the air is rate of the heat rejection is around 40 milliwatts. So in a second, it is giving out 40 millijoule of the energy. And in the question, they have mentioned that air properties that you need to use for this problem are the conductivity of air is 0.0274 watt per meter Kelvin. They have given dynamic viscosity, kinematic viscosity directly here. And they have given alpha also. Alpha, is K by rho Cp, right? So that value is also given directly. And Prandtl number for the air is given as 0.705. And they have given also Nusselt number correlation they have given. So if they directly give you something like this, you assume that flow is mostly turbulent. So that's why you can neglect the laminar part. Otherwise, your calculation will become very complicated. Now we need to find surface temperature of the fin at 15 mm from the base. So if this total length they have not given, They should give, right, L. Otherwise, how will you calculate? 1 second. What is the value of L? Yeah, apart from that, they have given K of aluminium, because the fin is made up of aluminium, as 200 watt per meter Kelvin. This K is for air, which is flowing over the aluminium fin. I am not sure what is this L. They should mention L, right? They have given it, I think. One second, I'll find out this L. So L should be, L is 1275. Okay. Yeah, so actually this total length itself is 15 mm. So basically you need to find the surface temperature at this end of the fin, and they have mentioned that assume insulated tip for the fin. So the problem is like this. Yeah, so everything is given here. Now let's see how to solve these type of problems. So first of all, calculate the Reynolds number at your x equal to 15 mm. And what will that be? That will be u infinity into x divided by your kinematic viscosity, right? So if you do this calculation, okay, I'll do that. 10 into x is 15 mm, right? So 0.015. So 0.15 divided by u is 24.7 into 10 to the power minus 6 divided by 24.7 into 10 to the power 6. So you have Reynolds number as 7072.87. And then you can calculate Prandtl number also, because you need it in Nusselt number. So mu Cp by K. Oh, actually it is directly given also. No need to calculate. So now you can go ahead and use it in your Nusselt number equation expression. So Nusselt number is local Nusselt number. It is nothing but h into x, or here it will be L, right, because it's the total length of your fin, divided by K of fluid. Okay, now here people will get confused. Sometimes, in fins you use K of fin, but in calculation of fin transfer coefficient you must use K of fluid. Otherwise you will make a mistake. So you can put 0296 into this. Already we calculated everything. Raised to 5.705 raised to 1 by 3. And you can put this as 0.015, and K of fluid is also given, which is 0.0274. And if you put all those things, you get H value as 67.7 watt per meter square Kelvin. So this is what the new part is. Otherwise, after this, everything is same that we already did for fits. So now you need to calculate M, which is under root HP by Ka, right? Here it is K of aluminium. So please note this point, otherwise you make a mistake. And now see, P is what? It's a square cross sectional area, right? So P will be 2 into 4 plus 4. So 16 mm perimeter, right? And your cross sectional area will be 16 mm square. Now you already know H, K is also given in the question, which is 200 for aluminium, and you can get the value of M, and M comes out to be 18.99 meter. I am writing meters here because otherwise, if you just write M, people may get confused with the M on the LHS. So now we know from previous class that for an insulated tip, one second. T0 minus T infinity, right? Yeah, the the thing is, for an insulated tip fin, we know, right, this T minus T infinity upon base temperature minus infinity temperature is nothing but cos H hyperbolic ML minus X divided by cos H ML, right? This is the formula that we learned in the last or previous classes. This is cos hyperbolic, okay? Don't confuse with, somebody may confuse this with heat transfer coefficient. Now here x is equal to L, right? So this numerator will become 1 because it is a cos hyperbolic of 0. And then it is just cos HML, cos hyperbolic of ML, because you are you need to find T at x equal to L, right? So if you do that, now here the problem is you can use, see, uh, this side of the equation is known because you know M, you know L. So cos hyperbolic ML known, this side is known. T infinity is known. But the problem is T naught is not known, right? What is the base temperature? So to do that, they have given one additional information in the problem, right? Which is uh, your, what you say? The heat transfer from the fin to the surrounding is 40 milliwatts. So you have to use that to get T0 first. And we knew the formula for heat transfer from the fin, insulated tip fin, is nothing but under root HPKA into theta 0 minus theta infinity base temperature difference into tan HML, right? Tan hyperbolic HML. So here they have given this as 40 into 10 to the power minus 3 watts. You know all these quantities, H, P, K, A, everything is known. Here K is K of fin. T infinity is 27. M is known, L is known. So this will also be known. So from here you should get T0. Okay. And if you do those calculations, I'm skipping the calculations here because it's straightforward algebra. If you do that, you get T0 as 52.383 degrees Celsius. Please verify this solution. And now you put this base temperature in the temperature distribution formula, and therefore you get T your T at x equal to L is nothing but T infinity plus T naught minus T infinity into 1 by cos HML. So this will be cos hyperbolic of ML. So all the terms on left hand side are known. Now we can plug the values and you should get the answer that your tip surface temperature at your tip will be 51.45 degrees Celsius. You should get. So if you notice, the base temperature is 52.4. Your tip temperature is 51.4. So almost your what you say, your whole of your fin is almost at isothermal condition. 1 second. Okay, so if you understand this question, you can solve your assignment question also easily. And yeah, so apart from that, let's see what else we have. Okay. One second. Yeah, so this is an interesting question. So what this question is, there is a refrigeration truck, a refrigeration or refrigerated truck, not it's truck which has refrigeration system on board. Refrigerated truck is moving on a highway at 90 kmph. So its speed is 90 kmph, where ambient temperature is around 55 degrees Celsius. So this is pretty hot ambient actually. This is a maybe desert area or something like that. And model truck body as a rectangular box of 11 cross 4 cross 3 meter, and they have given a block diagram for truck. So basically it looks like a big square, a big rectangle box. Let's say these were the wheels, and let's say if this was moving in this direction, this is your 11-meter length, this is your 3-meter height, and this width is 4 meter. So you should model this truck like this, is what they are saying. And so okay, so far so good. And now they have mentioned additional information. Consider boundary layer on 4 walls. So they have mentioned which walls. So see, you can guess also, right? Because air is coming at this U infinity, which is 90 kmph, right? So where the boundary layer will grow? It will be first on this side, and bottom, and at the back. Not here, at the back side, the wall which is not visible in this area. So on these 4 walls, there will be boundary layer, right? Maybe I'll use different color, otherwise it's getting confusing. So this is the first wall, this is top wall is the second, bottom wall will be the third wall where your boundary layer will be there, and fourth wall is behind this projection. It's not visible in this view. So there are 4 boundary layers developing on this truck as it moves in the air at 90 kmph. Okay. And next information is the wall surfaces of truck need to be maintained at 10 degrees Celsius. So there is something inside the truck which it needs to be kept cool, and that temperature requirement is 10 degrees Celsius. Then for some other properties for air are given. So so they have given density as 1.165 kg per meter cubes, Cp as 1.005 kilojoule per kg Kelvin, thermal conductivity as 2.673 into 10 to the power minus 2 watt per meter Kelvin, kinematic viscosity as 16 to 10 to the power minus 6 meter square per second, Prandtl number as 0.701, and find the following. So with this information, we need to find the following things. First, heat loss from 4 surfaces, because there will be heat coming from the hot ambient to the truck. So to maintain the truck at that temperatures, you need to keep on cooling it, right? And there will be heat loss from ambient to actually heat loss from four surfaces. It should not be like that. It should be heat transfer from four surfaces. Sorry. So first is this, you need to find heat transfer. And second is power required to overcome resistance acting on four surfaces. So these two things you need to find. There are other parts to this question, but I'm skipping them. They are understood. So now, first of all, what you do, you go and check the Reynolds number first. So Reynolds number, let's say we'll check for the whole length. So one second. Yeah, there is one important this detail. This assume turbulent flow. So they have mentioned that turbulent flow on the surfaces. So uh, you can, I mean, you can calculate Reynolds number also, and if you do that, you'll get something of the order of 10 to the power 7. So that itself is a turbulent flow. But then again, the question comes, what should we do? Because you can take some part of the surface as laminar initially, then you'll take the rest of them as turbulent. But here they have mentioned that you can assume the turbulent flow. So what that basically means is you can neglect the small part where the flow is laminar, because that length will be very small, and then you can assume the whole plate as having turbulent flow boundary layer. So in this case, you can calculate the result number, or this is like actual average result number over the surface. So that will be 0.036. So this is what we discussed in the section where we discussed correlations. So this is 0.037 actually. Into Reynolds number power 4 by 5 and Prandtl number power 1 by 3. You can calculate Reynolds number because we have density. You have velocity also here. You can convert this 90 into meters per second. So that is typically 5 by 18 you should multiply to get it meters per second. So that will be 25 meters per second velocity. And then these properties are given. See, this is given. So basically you have to multiply velocity into this, into the length. So all four boundary surfaces will have length of 11, right? Total length. So you can do that way. So 0.037 into density is 1.165, or directly I can take viscosity, right? I don't need density here. So U infinity into 11. 11 is the length of your plate or one surface parallel to the flow, and then divided by the kinematic viscosity. So this will be a Reynolds number power, and the Prandtl number is given as this. So if you do this, you'll get value which should be 19658.191. So this is your average result number. And we know that the result number definition is average heat transfer coefficient into the length divided by K of fluid. So K of air is also given in the question, 2.673 to the power minus 2. So if you just use L as 11 meters, you should get average heat transfer coefficient of 47.78 watt per meter square Kelvin. Okay, and now heat transfer from 4 surfaces of truck is nothing but total heat transfer is average heat transfer coefficient from each surface, total area of heat transfer into delta T. So average heat transfer, so total area is A1 plus A2 plus A3 plus A4, right? And delta T. Delta T is nothing but 55 minus 10, because ambient has 55, truck surface is at 10. Now this A1, A2, A3 you can calculate, right? Because all of them has one side which is 11 meters and only the other two sides change, right? So therefore it will be h bar into, you can just take 11 common, you'll have 4 plus 4 plus 3 plus 3, like that, and this is your delta T. So you can just plug in all these values for h bar, area, and delta T. You'll get heat transfer of 331.115 kilowatt. So this is the first part of the question. Now coming to the second part. So see, what they are asking in the second part is you need to find power required to overcome the resistance acting on 4 surfaces. So when they say resistance acting on 4 surfaces, they are talking about the drag resistance, right? Because when the vehicle moves in air, air will try to stop it, right? Because of its viscosity, and that is what results in the drag on those 4 surfaces, which are parallel to the flow of the air on the surface. So we know they have this CF. Did I mention this CF here? One second. Yeah, so this CF is actually local, but if you want to do it average, I think it is 0.0. One second. Yeah, I'm not sure. I should not say this. So in this question, they have mentioned that yeah, like here itself they had given in this part of the question. I forgot that you have to use this correlation for CF. So basically, Nusselt number and CF coefficient correlations were given in the problem. So here also you need not remember everything. So something like this. The point is not this, okay? The point is, every, like in this type of problems, the method is same only. If they give correlations, it's well and good, use them. If not, you just calculate the Reynolds number and find laminar, turbulent, whatever it is, and use the correlations. So here it is all turbulent, so we use Nusselt number, which is turbulent average Nusselt number, and average this the drag coefficient is 0.072 divided by RE power 1 by 5. 0.5 is basically 1 by 5. So if you calculate Reynolds number, you should get 17.2 into 10 to the power 6, and you need to take 1/5 power of this. If you do that, you'll get 2.57 into 10 to the power minus 3, and this will be dimensionless number because it's a coefficient, so it will be dimensionless. And then drag force, how do you calculate? We know that this drag coefficient is nothing but wall shear stress divided by half into rho infinity square, right? And wall shear stress is nothing but drag force into the total area, right? Or divided by total area, because its shear stress is Newton per meter square. So that should be force divided by area. So now we have total area, we have this properties also, and we know this also. So if you plug in this, and again total area will be calculated similar to what we did here. So that will be your total area, because drag is acting on those four surfaces. And if you calculate, you do the algebra, you will get drag force as 144.09 Newton. But now go back to the question. In question, they are not asking about drag force. What they are asking here is, what is the power required? So we know that power required is nothing but drag force into u infinity, because this is the velocity against which we are doing the work. So that is nothing but 144.09 into 25. So you will get 3.602 kilowatt. And this is your answer. So this is a question where you used almost all the concepts that you learned, and it's a like practical question also. Usually you will not have a truck with 10 degrees Celsius wall and it is openly going in a desert. Typically there will be insulation around the truck if it has a refrigeration inside, but still there will be some heat loss because of the heat leakage from the insulation of the truck walls. So typically, that can be also one next level problem. So instead of directly giving you the surface temperature, one can mention that inside the truck it is 10 degrees. Then there is a wall thickness of, let's say, 10 mm, and it is lined with some insulator inside of certain thermal conductivity and certain uh, thickness. And then you need to first find the surface temperature, and then you need to find the other things which are like power, etc., etc. So that can be also one of the variation of this problem. It is not yet asked, but it can be asked. You never know. Okay. So yeah, since like there was another topic which was regarding the, see, this internal pipe flows and all will take next class, because uh, it's new topic and it will continue to the next week also. In between there was one topic of cylinder, flow over cylinder. We'll take one question about that. But one more thing that you should remember about it is the angle at which flow separation happens. So for laminar flow it is 80 degrees, and for turbulent it is 140. In some exams they directly ask this question. I think in GATE exam they had asked previously at what angle the laminar flow separates from something like that when it is flowing over a cylinder. So these factual questions, if you know, you know, otherwise you don't know. So you should remember this. We'll take one question and we'll close for today on the cylindrical thing, flow over cylinder. So, so there is a cylinder like this. Sorry. Yeah, so there is a cylinder like this. Maybe my drawing is not that good, but let's assume it's a cylinder. And there is a water flow over the cylinder like this in this direction. So water is flowing over the cylinder. Water is at 20 degrees Celsius, and it is flowing with bulk mean velocity of 1.5 meter per second. For this tube, diameter is 25 mm, or cylinder, whatever you want to call it. Surface temperature of cylinder is constant, maintained at 80 degrees Celsius. Then these properties are given for water, etc. So I'll just list them down. And usually the properties are typically given at mean temperature. What do I mean? So when water is at 20, surface is at 80. So if you take mean of them, it will be 20 plus 80, 100 by 250. So the properties of water will be calculated at 50. Even properties of cylinder also, if something is required, they'll be calculated at mean temperature. So properties of water at 50 degrees Celsius. CP, we should always already know water has very high CP, which is 4.1813 kilojoule per kg Kelvin. Kinematic viscosity of water is 0.568 into 10 to the power -6 meters square per second. Thermal conductivity 0.6395. Watt per meter Kelvin. Prandtl number is given directly as 3.68. Density of water is 990 kg per meter cube. And again, they have mentioned dynamic viscosity of water at 80 degrees as 3.54. One second. Okay. I'll explain the significance of this viscosity data in a second. Just let me write down all the data that is given. And they have mentioned that use correlation, which is your average Nusselt number is 0.4 RE power 1 by 2 plus 0.06 RE power 2 by 3 into Prandtl raised to 2 by 5 into mu of water at 80 degrees Celsius divided by mu of water at 20 degrees Celsius whole raised to power 1 by 4. And that is why they have given this data. So this is additional term that is they have mentioned in this coefficient Nusselt number correlation, and it requires this. So again, there is no hard rule that why did this, one second, why did this term came here. No, nothing like that. They did some experiments and they would have found out that water viscosity plays important role at temperature, various temperatures, and that's why they included this term also here. Now we need to find average heat transfer coefficient first, and then Q heat transfer rate per unit length of the tube. So two things we need to find, and I think by now you may be familiarized with what we are going to do. First is So here they have not mentioned whether it's laminar or turbulent, whatever it is, and you don't care also because you directly have this Nusselt number expression, right? So what you need to do is you need to directly put everything in there and you get the H bar or average heat transfer coefficient. So see here everywhere they are using Reynolds number, right? So you can separately calculate it. You can directly plug in also, it doesn't matter. So now here the trick is, since it's a cylinder, usually we take rho u infinity by L by mu, right, for a flat plate. But it's a cylinder, so here the characteristic length scale is here diameter of the tube or cylinder, whatever it is. So that is there. And they have given kinematic viscosity, so you can just take kinematic viscosity to get the Reynolds number. So 1.5 meter per second was the u infinity. Diameter is 25 mm, so it will be 0.025 meters, right? Viscosity, kinematic viscosity was 568 into 10 to the power minus 6 meters squares per second. So that gives you Reynolds number of 66021.12. Prandtl number directly given 3.68. Mu at 80 and 20. So this ratio also you can directly calculate. So you put everything in the Nusselt number expression. You'll get average Nusselt number. It is nothing but H bar, average heat transfer coefficient, diameter of the tube into K of fluid is nothing but, then you have to put all the values here. So the first term will be 0.4 into 66021.12 raised to half plus 0.06 into 66021.12 raised to what is it, 2 by 3 into Prandtl number is 3.68 raised to power 2 by 5, and these values I can just write 0.35456 divided by 1.006. That into 10 to the power minus 3 will get cancelled, right? And it will be raised to 1 by 4. So, and this diameter is 0.025 mm. K of fluid is also known, which is 0.6395 watt per meter square. So if you plug in all these values and if you do the calculations properly, you should get H bar, which is average heat transfer coefficient, as 438.84 watt per meter square Kelvin. Oh, sorry. This is your Nusselt number. Sorry, this is your average Nusselt number, and then your H bar, which is heat transfer coefficient, is 11225.53 watt per meter square Kelvin. This will go away because it's a non-dimensionalized number, and this is your answer. Okay, you can cross-check this data calculations, and you should get this. Now, what is the heat transfer rate? It is nothing but average into area into delta T. Now, what is the area for tube? The contact area between tube and the fluid is 2 pi or pi d into L into delta T, right? L is not given, therefore they are asking heat transfer per unit length. So you will have H bar pi d into delta T. So now delta T is your what you say your surface temperature of tube minus infinity. So you can plug these values into pi into 0.025 into 80 minus 20, right? What is your T infinity? Yeah, 20. So 80 minus 20, so that will be 60. So if you do the calculation, I'll just quickly check. 60 into 0.025 into pi into 11225.53. So that comes around 52.89 kilowatt. So this is your heat transfer per unit length. So this will be per unit meter, kilowatt per unit meter. Okay. So I hope the methodology is clear. As I mentioned many times, it's typically first calculate Reynolds number or check whether the correlations are given. If correlations are given, then your life is easy. Then calculate the Reynolds number. If correlations are given, directly use them and get the average heat transfer coefficient or local heat transfer coefficient depending on the question. Otherwise, first you calculate Reynolds number, then you look for the suitable correlations, and then it depends what is asked in the problem. Sample problem will have H bar calculation, then heat transfer calculation. These fin problems will have first you need to calculate H bar, then use that H in the fin formulas to get the fins. Or there will be some comparative questions where they will give you two properties or two different separate fluids, etc., and then you have to compare. Then there can be another set of questions where what you do, you have, let's say, one parallel flat plate and you have a flow over it, and then they'll say that fluid viscosity is doubled. Then what is the heat transfer coefficient? So basically, you have to use the Nusselt number correlation, and there you just see that H bar is proportional to what power of that variable, and you just calculate. So those type of questions can also be there. So I think we covered most of the things here. Internal flows will start from next class onwards, because then it will be like wholesome discussion. Right now it will be piecewise, and then we'll see. Okay. So for now we'll stop, and thank you everyone. See you next time.